Hey, welcome back. In this video, just solving another 3D statics problem. So in this case, we have this sort of plank here that's green, and it is connected to a wall here with a hinge. This wall is right in the YZ plane. And then also, from its center line, it's connected with this cable over to this other wall. And this wall is right in the XY plane. You'll notice that the center line of this plank, I've drawn it so that it's one unit over in the positive Z direction. And I just drew it that way so I could kind of set up my walls right here in these planes to make it nice and easy for us. Alright, what we want to do here is we want to figure out what is the tension in this cable and also what are the reactions here at this hinge. And we can do that knowing everything we know about this problem. So the first thing that we need to do is draw a free body diagram. So now looking at the coordinates of B, it's halfway along the plank here, so it's 2 meters down the plank and it's in the center line. So its coordinates would be 2 cos 30, negative 2 sine 30, and 1. Then the next step in finding the direction that this tension is oriented in would be finding the position vector from B to D, and then subtracting basically just from the coordinates of the head minus the coordinates of the tail. So now we have the position vector from B to D in vector form. And the next thing that we'll need to get is its length. And so to calculate the length of it, of RBD, we just have the square root of this vector dot itself. Okay, so the next thing that we have to do is find the unit vector of the tension, and so that will be EBD. And to do that, we have to just divide the position vector RBD by the magnitude of the position vector. And now that we know the unit vector, then tension in vector form is just the unit vector times the magnitude of the tension. Okay, now that we have tension in vector form, now we have some expression for all of the forces that show up on a free body diagram, and now we can solve, or now we can write the equations for the sum of forces in the three directions. So, for the sum of forces in the x direction, we will have the x component of the reaction force at A, so we have AX, plus the x component of the tension force, and that's this guy, so that is plus 0.084 times T. And that, because this guy is in static equilibrium, is equal to 0. Then for the sum of forces in the y direction, we are going to have the y component of the reaction force at A, so we have AY, plus the y component of the tension force, so that's this guy, we have 0.945 plus 0.945, make sure that doesn't look like a 945 times T. And then we also have to subtract out this guy here because this was our applied force, so we have minus 200 newtons. And again, all of these units are in newtons, so that's equal to 0. And then for the sum of forces in the z direction, we just get the z component of the reaction force at A, so we have AZ, minus the z component, or you add in the z component of the tension force, and it happens to be negative, so it's minus 0.315 times the magnitude. And again, that's all equal to 0. Now the next thing that we need to do is we need to write our equations for the sum of moments about the x, y, and z axes. We can condense all of those into a single expression for a sum of moments about a point. And that is going to be easiest if we have our sum of moments about A, because we have a lot of stuff going on at A, and if we choose that point to have sum our moments about, we can eliminate AX, AY, and AZ from those expressions. And then we'll only have the moments acting at that point and also the two other applied forces. So to do that, we're going to need the position vector from A to B, and we're also going to need the position vector from A to C. So the sum of moments about A will include this moment, MAY, this moment, MAX, and it'll also include the moment about A caused by this tension in T, and also the moment about A caused by this applied force. So to write that down, it looks like this. Then if we just expand these out, we will get, and the reason I wrote MAX like this and MAY like this is because MAX only has a component in the x direction, and same as MAY only has a component in the y direction, so that's why you're seeing them like that. Okay, so now what we need to do is we just need to expand out these second two terms and apply the cross product, so that looks like this. And I guess I really should have set these all equal to 0, just like that, because really the sum of moments is 0 when it's in static equilibrium. And then the reason being is when we separate this out into the sum of moments of both the individual x, y, and z axes, then we get these expressions. And all I basically did is I just took this line as the x component of this moment, and so that just makes it the sum of moments about the x-axis. The second line is the sum of moments about the y-axis, and the third line is the sum of moments about the z-axis, and so you're seeing that down here. One thing I should do is I will just go back up here and grab these guys. So these were our three equations of equilibrium for the forces. Now down here we have three equations of equilibrium for the moments, and together we have our 6 equations of equilibrium now. Now all we can do is we can just simply use substitution and we can start solving for things. So right away, looking here, we're going to be able to solve for the magnitude of the tension using this guy. And now that we know that the tension is 402 newtons, we can just plug that back into all these equations, and then we can solve for MAY and MAX. So we get values here for MAY and MAX. MAZ turns out to be 0. If you do this exactly, it's not exactly 0, but that's just because of some of my rounding that I've been doing through this problem. But that's good because we don't want that moment appearing about the z-axis, right? Because this hinge wasn't capable of providing a moment about the z-axis. All right. The last thing that we just need to do then is, again, we have tension, so we can just plug it into the equations for x, y, and z for the forces, and then we'll just get our reaction forces for AX, AY, and AZ. So there we go. We've now solved for everything the problem asked us to solve for. All of the reaction at A, so the 3 reaction forces and the 3 moments. Note that one of them was 0, and that's exactly what we expected, and that we also solved for the tension in the cable here. So hopefully that was all helpful, and I will see you guys in the next video.